Hello, my name is Tom Tremblay. I'm the Global Design, Lifecycle, and Simulation Industry Manager for Autodesk Post-Secondary Education. In this session, we're going to briefly review the process for preparing for certification, but we'll spend most of our time reviewing the certification objectives for Autodesk Inventor in the context of a workflow. At the end of this webcast, you'll be able to identify several of the options available for preparing for certification. You will have reviewed the certification objectives using examples, and you will be able to begin preparing to take the exam, whether it be at Autodesk University or on your own. There are many reasons to get certified. For me, the most valuable is personal. I want to be able to measure my skills with Autodesk Inventor against a validated, secure, and rigorous test that causes me to explore the boundaries of Autodesk Inventor, not just the tools that I would typically use in a given day. So what is the process of getting certified? Well, the fact that you're watching this webcast is a very important first step. One thing that I highly recommend is taking a look at the certification preparation materials that are available at autodesk.com/certification, as well as the certification manuals. Once you've reviewed those objectives, take any existing training or review online tutorials or certification training materials that are available to you to fill in whatever gaps you may find in the objectives. Many commercial users don't use all of the product, of course, so there are certain features and functionality inside of Inventor that you may not have used in your day-to-day work. Then, of course, take the exam. If you're coming to Autodesk University, you'll be able to take the exam at no cost. Finally, display that certificate. It will have a number that will be unique to you, and if need be, someone can research and verify your certification in the product. Now let's take a look at the certification objectives. For project files, let's focus on how to control a project file, really looking at things like pathing and other information that is commonly overlooked by users. A project file is simply just a text file that allows Inventor to know where to look for files and where it should put files when you go to save it. In this case, we'll create a new project file, a single user project file, and we'll give it a name. The important thing to do is to make sure that after you've given it your name, that you want to select where the workspace folder is. This is not only where the project file is stored, it determines the top level of where your data is stored. All data should be stored under this level. Now that we have a new file, it's been added to the list, and we can now create shortcuts or aliases for common folders that we'd like to go to. For example, assemblies. We just simply put in the shortcut name, and then we can go find any length of path that we want. All we'll have to do in the Open dialog box or the Save dialog box is simply find that shortcut. We can add additional paths if we like, and we can add as many as we like. Once we've added a few of these, we can also go to the lower right and control what libraries are available to this project file. By deselecting them or reselecting them, we control which Content Center files are available. We can also control where the content will be placed if we use it. For example, if we place a 1/4 20-inch bolt or an M10 by 35 bolt, we can use this path to determine where that bolt will go. In a workgroup environment, this can be essential to keep people from not being able to find files when they open an assembly. Now that we're done with our project file, we'll go ahead and save it and be able to use it to access all of our data. For the user interface, we want to identify how visual styles are accessed and can be controlled to change the appearance of a model inside of the design window. Inventor interface has a lot of components. Some of them will be familiar with previous versions. For example, the view cube allows you to orient to a corner or an edge or a face, to directly orbit the model just by dragging the cube. The navigate bar on the right allows you to access tools like orbit, pan, or zoom, which are also available through the keyboard shortcuts. One thing that's new to Inventor 2012 is the marking menu. There are two modes. The manual mode allows you to right-click and then click a tool. the marking mode, you just simply right-click, drag over a tool, and it will start that tool. By choosing different tabs, we can access different tools. Here in the View tab, we can access visual styles, one of which, for example, is shaded with hidden lines, a very popular option. Another one to remove all the color is monochrome. My personal favorite is watercolor. Gives you a slightly different effect than you're probably used to in a mechanical assembly, but nonetheless, it communicates some different ideas. Finally, let's take a look at illustration, which allows you to have more of a hand sketch feel. The realistic mode in 2012 is different as well. It now engages not only the Autodesk color palette, but it also engages ray tracing. Let's go ahead and move to perspective mode so we can get a little better feel for this. Starting to look very good. You can see parts reflected on other parts. We can also turn on our shadows in order to get ambient shadows, ground shadows, part shadows, and even reflections off the ground. Now the reflections are oriented based on the position of the top of the view cube. Let's engage a visual style environment. In this case, since we're working with a small model, the empty lab is a great choice. As you can see, the ray trace updates. Now this is the interactive mode. Good and best will give you a much better result. All right, this looks great. Let's take a look at the next objective. In sketching, you want to understand how to create and control dynamic input dimensions, as well as use sketch constraints. Inside of the sketching environment, as we're drawing, we're given feedback. This is known as dynamic input. These dimensions will tell us what our length is, what angles might be. As we enter values, we see we can make these lines precise. For example, as I enter a length for this line, I'll see a little padlock symbol that lets me know that I've modified that. As I continue to sketch, I'll get feedback on sketching constraints such as horizontal or perpendicular. I'll get inference lines that let me know when I'm over another object so I can more closely lock in on it. And as I move near objects, I can scrub. What scrubbing does, or gesturing does, is it allows me to establish what priority the constraints will have. Now that we've defined our sketch, we can now start to make modifications on it. For example, let's start to take a look at the constraint system. For example, it will highlight perpendicularity, parallelism, the fact that that line is horizontal. All of the icons match up with the icons in the ribbon as well. If we make modifications, we can simply delete dimensions or place dimensions later on. We can see our degrees of freedom of the sketch so we can better understand how this sketch is going to behave. As we start to apply more constraints or more dimensions, these degrees of freedom will disappear. For example, the angular degree of freedom on the line on the right. We can assign horizontal constraints between the center point of the sketch and the vertical edge, or vertical constraints between the horizontal line and the center of the sketch. That will effectively center this rectangle on the origin of the sketch. We can create equations or change the dimension values and update things. We can link dimensions. For example, here I can say that that dimension should be equal to the first dimension and update it. We can still make modifications to the source dimension as well. In this case, we'll edit the 60mm dimension, tell it that its name is not D0, but width, and its value is 100, and you'll notice that the other line still updates to follow suit. Part modeling is of course a very large topic, and you'll see there are a number of objectives around creating a pattern of features, being able to place a shell feature, being able to use extrude features, hole features, revolve features, and even create work features. We'll also need to understand how to project geometry and use the project cut edges commands. So here we have our sketch. All I have to do is select an edge and I get the most common tools: extrude, revolve, or edit sketch. And simply drag the value of our extrusion height, or we can type in a precise value to get the number that we want. We're able to tell it to go ahead and place this. Now, something that's very important is to know where to get your properties. So by right-clicking on the object in the browser, we can select our material if we need to change it. And of course, here we have the mass properties as well as the properties for our center of gravity, which are going to be very important for taking the test. We can change the material, but we can also change the color of a component to make it look a little different or something more appealing to us. By selecting a sharp edge, we get the most common tools, fillet or chamfer. That's typically what you do in a machine design environment for sharp edges. So we'll select the various edges and we'll place an edge fillet just by simply dragging the value. Notice that the preview goes to wireframe when we can't get that edge to generate. Place these fillets, and then we're able to go ahead and keep making other changes. In this case, we have a sketch defined where we can again use our revolve tool. We have to select the axis, and then we can create a full revolve, or we can enter a partial by entering just an angle. We can also switch that back to a full and get our completed feature. Next, let's take a look at how we can take an existing sketch and project it onto a face using the Project 3D Sketch tool. So by selecting the face that I want, I can take the geometry that's in my active sketch and apply it to another face to be used for a feature later on. Now let's take a look at the shell tool. The shell tool has some interesting options. We can thicken to the outside, thicken to the inside. Here I'll select one thickness value, and for a particular face, in this case the green face, I'll tell it that I want a different thickness value. When it's done, you'll see that the entire part has been thinned to 5 millimeters except the face based on the green face, which is 15 millimeters. Let's place some hole features. The hole feature has a lot of different options: counterbores, countersinks, spot faces, and drilled holes. We can also just position holes. We can roughen their sizes just by dragging them around or dragging the diameter. We can also switch to a different type of hole. For example, here with linear placement, I can use dimensions to place this hole. I'll say I want it counterbored. I'll also say that I want a clearance hole. So I don't have to look up the values for an ISO, let's say, socket head cap screw of a certain size. For an M4, it will tell me what the standard counterbore depth, counterbore diameter, and drill diameter are. And I can make modifications if I want to, or locate it as I've done in this video. Now, next, let's go ahead and create a pattern. In this case, we'll just use the rectangular pattern tool. I'll select the hole, and I'll select the edge for direction 1. It's important to note with the rectangular pattern tool that you really don't have to just restrict yourself to rectangles. It's really just any two directions. In fact, they can go opposite of one another as well. We'll put in the number of columns or rows if you're an AutoCAD person, the distance between them, and we'll place our features. If we orbit around here, we can see one of the features is in a place where we really don't want it. So we can expand our rectangular pattern, find the occurrence that we want, and simply suppress it so that it's no longer generated inside the model. Next, let's do a few other functions. For example, I have an extruded surface that's based on a sketch. If I go to do a slice graphics and look at this sketch, I can see where the edges were projected into the sketch regardless of what angle or what draft was there. That's using project cut surface as an option. Let's go ahead and replace one face with the surface that was extruded from that sketch. And we'll see we're able to put a curved face in here. Next, let's create a work plane. Of course, we have work axes, work points. This work plane, we're going to go ahead and create offset from an existing plane. So we simply drag our value in, or we can enter a precise value to put that in. And we'll use that plane as a basis to start a sketch on top of our part. From that sketch, we'll go ahead and create a cylinder. Now, this cylinder is going to have a small problem, is that since that sketch was essentially tangent to the top of this, the cylinder we extruded out has a gap at the base of it. This is another option one of our fillet tools can solve by using the face fillet. The face fillet allows me to select any two sets of faces, and it will simply fill that geometry in with a fillet feature. It will even offer me a suggested radius that will work. I can refine that if I like. and it will update the preview. When I'm satisfied, I place it, and it goes ahead and generates the fillet. With assembly modeling, we need to apply and use assembly constraints, create a level of detail, create a part in the context of an assembly, describe and use shrink wrap, create a positional representation, create components using design accelerator commands, modify a bill of materials, find a minimum distance between parts and components, and then use the frame generator command. Now let's take a look at our assembly. First, let's place some assembly constraints. Using the make constraint, which is an oppositional constraint, it will take the two blue faces and stick them together. Let's orbit our model around and let's find the yellow faces. Again, using the mate solution for the mate constraint to bring those two faces looking at each other. Then let's close this out for a second and see what's going on. So we still have a remaining degree of freedom on the purple part. We're going to remove that by applying a flush solution of the mate constraint, which will align the two faces on the side. Now that we have this, let's go ahead and take a look at some other constraint options. A very common one is to take holes that are in parts and use those. In this case, we'll use the insert constraint to align both the plane and the axes of our two parts. Then finally, let's use the last of the big assembly constraints, which is the angle constraint. We'll select two faces to align, and then an axis to pivot about, and set the value, and that lines things up. Now let's move on to some of the more advanced constraints, such as tangent. That will just simply align the blue faces so that they ride each other tangent. You have an internal and an external solution for that. Now let's do something a little fancier, a transitional constraint between the yellow faces. So similar to tangent, but with more complexity, it will go ahead and ride that splined interior contour around our body. Let's take advantage of the content center. Mentioned before, there are over 1 million parts in the content center. Let's just go find one. For example, under the hex head bolts, let's expand that and go down and say find an ISO 4017, a nice hex head bolt. It drags a preview on the screen. As we hover over an edge, it will update that preview to fit the hole. We simply place it. We can take a closer look, and as we drag this, we'll see that it even drags that out based on standard sizes. We can't just randomly pick a size here. That's a great way to prevent causing problems in production. We'll place that, and we'll have that locked into location. Now, another way to approach this is instead of placing content center, let's use the bolted connection generator, which is one of the design accelerators. First, we'll tell it where we want it to start. So we'll tell it to start on the yellow face of the purple part, yellow face of the purple part, and we'll tell it how we want it located off of what edges. We can then tell it if we want it to be a blind or through hole. Since it's a blind hole, we want it to start on the first face of the red part behind the purple part. We'll set in our distances or our locations for where the holes will go. Now, there were no holes in the red or the purple part. Instead, what we're going to do is kind of put things in their proper perspective by saying that we need to use a bolt to hold these two objects together. We'll select which type of bolt it is, and by the way, it will filter out our options based on the length of the fastener and the diameter. So here we'll tell it how we want it sorted. We can drag out the depth of the hole. We can also drag out the length of the fastener, and you'll notice the hole will follow it. When we go to place this, it will not only place the bolt into our assembly, it will go ahead and modify the assembly components themselves. So if I go to edit one of the parts, I see everything's constrained. If I go to edit the red part, there's a tapped hole now in that red part where there was none before. Let's take a look at another design accelerator. So from the Design tab, I can select the bearing calculator. Now, this happens to be a bearing generator, pardon me. The generator creates geometry. A calculator, such as the weld calculator, will only tell you what size you need but then you have to create the geometry. In this case, we'll roughen some sizes. We can update our database or go select the type of bearing that we want. There's a massive selection options. When we update based on the physical size, it will tell us what bearings physically can be used. We can also go into the calculation, tell it what sorts of stresses, speeds, life expectancies, and other engineering criteria are required, and it will further filter that list. In this assembly, let's modify the bill of materials. There are a lot of different bill of materials structures, such as normal, which is just a part that we might generate, purchased, which is a part we might purchase, and then we also have some other capabilities. For example, this status, which is phantom. So I have the grinding wheel and the two washers as a subassembly. Well, when we ship this out or when the shop gets these parts, they may not be looking at them as a subassembly. So I can make the subassembly a phantom that will raise those components up in the parts list. It will also allow me to edit those values. Now let's do some measurement. First, we can select any faces on the parts. We can also change our filter to sort based on component. So I say select the minimum distance between these components. In this case, the minimum distance will be based on the hearts of these components themselves. If I say based on part, it will allow me to filter through the subassembly structure to an individual part and find that minimum distance. Let's take a look at level of detail. For example, if I select the gears level of detail, it not only changes the visibility in my assembly, it changes how many files are active in memory. This is a very important thing if you're working with large data sets on limited hardware. Really learn what level of detail representations are. Here we have a level of detail representation called all content center suppressed, so it removes the nuts, the bolts, bearings, what have you. I'm going to create a new content center just called primary components. I want to filter this down. Right now I have 22 components on screen based on 22 files. So now that this level of detail is active, I can select a component, use my selection options, and tell it to find other components of that size. All right? Maybe I want to modify that selection and make this slightly larger. By hitting the checkbox, I'll select any of those components, and by using suppress, I'll remove them not just from the screen, but from memory. So now I had 6 parts visible based on 7 files. Let's take a look here at some constraints. For example, I can see the value of this insert constraint between the light blue plate and the dark blue base is set to 0. It's an insert constraint. What I want to do, however, is I want to take advantage of some positional representations. For example, when I select the open positional representation, it shows me that that was overridden to 15 millimeters. Well, let's copy our closed positional representation and create one called fully open or full open. Let's activate it. Then let's select that insert constraint and override it with a new value. Let's say 35 millimeters. We'll say OK, and you'll see that that brings this way out to the edge. All right, that looks good. Now we have an assembly. What I want to do is I want to take out some of the detail of this assembly. I'm going to be exchanging it with others, and I don't want them to see all of my intellectual property. So I want to simplify this geometry, so I will create a shrink wrap substitution. A level of detail representation removes parts from memory, but we can also create a level of detail representation based on a shrink wrap of a part. Now the shrink wrap tool allows me to go through and select geometry such as holes or openings and cap them based on certain information. For example, I'll set in my range of size of opening that I want to go ahead and use the hole patching function on. I'll set that value. Tell it to remove any geometry that isn't visible. For example, there's a heater core inside of this, there's a power supply inside of this, and I'm going to tell it to merge this into a single part file with no gaps between it. I can see how my part looks presently. I can preview this to see how it will look. And it will show me in yellow that it's going to be capping the end of the nozzles and the vents at the top of the assembly. So we'll be filling that information in. Let's go ahead and generate our shrink wrap. Now that's done, we can go ahead and take a look inside of this object by creating a section view. Off the top face, as I drag down, you'll see that there is no interior geometry. You'll just have to take my word for it that there was a power supply and a heater core in there. But you also see it's filled in the pipe fittings. So that's creating our shrink wrap. Now let's take a look at the frame generator. I have a frame here. I'm going to select a standard, the ANSI standard. I'll select a family of a type of tubing or beam section that I want. Then I can select a size for that. I can then go through and select the individual components that I want to place that beam on. I can also use a window select if I prefer. Now let's generate the metal frame components based on that skeleton. Once the frame components are placed, I can place additional frame components or start making modifications. For example, I have two components here that were placed based on the sketch, but they're not exactly how I want them. I want to go ahead and miter them together, and I can even include a weld gap in the miter. Let's go ahead and drop that in. You can see the clearance between the two components. There are a number of other ways to edit this by trimming to a face, trimming or extending a previously trimmed member, and other tools to suit your needs. Finally, for drawings, we want to be able to create and edit dimensions in the drawing, edit a section view, be able to modify a style in a drawing, edit a whole table, and modify a parts list. And of course, we have to be able to edit base and projected views as well. Here we are in the drawing environment. Let's place a base view. For a base view, all we have to do is select a part or an assembly, set the scale, the visualization style, and the point of view. Then we can place a bottom view, a side view, an isometric view, tell it to create, and it will generate those views. Very nice, very quick. Let's create a section view. To create a section view, we just have to draw a section line. We can also use a sketch to define a section line, or once we've placed a section line, we can edit it as a sketch and even add things like dimensions or arcs to it to create a more refined and more complex section. To make modifications to drawing views, we can do things like rotate views based by selecting an edge and telling it to be vertical. We can edit the visibility of hidden lines in a view just with a simple double click. We can realign drawing views. For example, in this case, we'll take our auxiliary view and align it to be vertical to our base view. If we double click on the isometric view, we can change properties involved with that view. For example, we may want to tell it to be shaded or a different scale. We just simply change it in the dialog box, say OK, and it updates the view. Now let's place some dimensions. The general dimension tool inside of drawings works just like the general dimension tool inside of sketching. One tool will actually do just about any type of dimension. So we can place a linear dimension, we can place a radial dimension, all just went from the one tool. If I come up to this front view, I can start placing a dimension, but if I come near this angled edge, it shows me that I can place an angular dimension. Or if I pick the side of this cylindrical edge, I can show a linear diameter, all from the same dimensioning tool. Now, there are times where we may want to create dimensions more rapidly. In this case, we can use a baseline dimension or a baseline set, select all of the members of the set that we want, and tell it to place them all at once. Another option, though not used as much in mechanical engineering as architecture, is to create a chain dimension. Essentially the same workflow as a baseline. You just pick the elements you want, it drops it in place, and we just create it. Very nice, very simple. If we like, we can go ahead and modify what standard or what style it's using. Now, to modify the style itself, you have to go into the standards options, and for example, to make changes to things like the text style of a dimension, you actually have to modify the text style that is fed into the dimension style. Here, let's place a hole note. You'll notice that only holes highlight. I can select it, and it picks up the fact that that is a tapped hole. A quick double click to edit the hole note, and I can tell it to insert a quantity for this hole note. I can insert other things like thread class or what type of fastener it is. In this case, I'll put in the quantity, and it shows me how many of that type of hole are in this drawing view. Let's place some retrieve dimensions. So what this allows me to do is going back to the original part model, find the dimensions that were used to create a particular feature, for example, the 90 millimeter diameter that bolt circle is defined on, and if I edit that dimension by telling it to edit the model dimension, change its value, it will go ahead and update the 3D part and therefore the 2D associative drawing all in one step. Now let's go ahead and make some additional changes. For example, here we have a drawing with a large number of holes. Rather than dimensioning each of them, I'll establish a datum and tell it to apply a hole table for this entire drawing view. When we take a close look, we see the X value, the Y value, the type of hole. In fact, you'll see we have several holes of the same description, so we can do things like combining notes or changing what types of holes will be defined in order to make our hole table easier to see. Here you'll see the callouts on the individual holes as well. Here in this assembly drawing, we can go ahead and add balloons individually, or we can auto balloon a group. We can tell it to show us a preview of the horizontal placement, the vertical placement, placing it all around the place. So here we were able to just go back to our horizontal. If we want, we can even change the spacing in between the balloons to spread things out a little more and go ahead and drop that in. If we add a parts list into our drawing, that parts list can be modified with a simple double click or a right click and to edit the parts list, but that parts list will pick up the balloon values. If I were to change, for example, item 23 to a different number, its balloon would update to that corresponding number. You can see we can also update the column placements and anything else to make our parts list look like it's supposed to. The topics you'll need to be familiar with for advanced modeling include creating a 3D path using the intersection curve and project to surface commands, creating a loft feature, creating a multi-body part, creating a part using only surfaces, creating a sweep feature, creating an eye part, creating and constraining sketch blocks, using eye logic, and being able to emboss text and a profile. Let's do some advanced sketching. In this case, I want to use the rectangular pattern to take a circle and just create a pattern with it. This is great because the rectangular pattern has the ability to pattern in two directions. They do not have to be in the same direction. Most of the time we would prefer to create something like a hole as a feature and then pattern that feature. However, if you need to create something that's a little more unique, or if your profile is something more complex than, say, just this circle, this is a great capability to take advantage of. If you're an AutoCAD user, you're probably very familiar with the concept of blocks. Blocks allow you to group geometry together and use them as a unit. The same thing applies to sketch blocks inside of Inventor. Here we have a series of predefined blocks called Link 1. We have 3 instances of it. And now we'd like to create another block. We'll take the pink geometry and create something called Link 2. So we'll establish the name, we could put in a description, we'll select the elements that are going to make up this new block, and we'll select an insertion point for it. All right, once this is done, we can just hit OK. And now you'll see it appear under the linkage sketch in the browser. Now, by applying sketch constraints, or in this case, just simply dragging point on point, and we'll do the same thing to the other end, we're able to take this simple 2D geometry and build a mechanism that we can test a concept with before getting into 3D. This is something that's often overlooked inside of Inventor. Now, just as you would expect with AutoCAD blocks, sketch blocks inside of Inventor allow us to go in, make modifications, in this case using parametric dimensions. And when we're finished making the modification, this may appear a little messy, but this will update as soon as we're finished. And now we're able to see the new version of our mechanism, and it works just as well as it did before. Let's go ahead and create a loft feature. You'll see we have a 3D sketch based on a projected curve and a 2D sketch just simply applied to the bottom face of a portion of this handle. We can tell it to loft along the center line, which we'll select directly from the window, and we get a great preview of what our feature will look like. Now, you may want to do a rectangular pattern or a circular pattern. In this case, I've already done a circular pattern, but I wanted to wait until the loft was finished. So I was able to use my end of part marker to roll up over the circular pattern of the entire solid. And now that I roll back down below it, it picks up the new lofted handle as well. This is a sweep feature. Sweep is made for taking a profile and passing it along a path. However, here I can implement a guide rail to add a twist to this sweep feature. Very easy way to create a complex feature. Here is a part. It's a simple drawer front. However, I need to make a number of them that have essentially the same geometry but in various sizes. This is where the concept of an eye part comes in. I add another row to my eye part definition. I go in and change the values of a few parametric dimensions, and I can even come in and tell it to go ahead and generate the single hole pull, find the value for the double hole pull under the suppression tool, add its column, and I'll tell it to not compute the double hole pull for this member of the family. When I'm finished, it will generate a table feature inside of my browser where I can see and quickly, with a double click, compare the two models. Very nice, very easy. Now, if we want to get a little more complex, we have the ability to tell it to just make modifications to one member of this family. So if I come back here and tell it that I'd like to place a fillet, I'll only be placing it on the active member. So if I were editing the family scope, adding this fillet would also edit any other members of the family. All right, now I've made my change. I'll say OK, and let's compare. Let's make sure that this is exactly what I want. I double click on the second instance and you'll see there are no fillets on the corners. Now let's take things to the next level. iLogic is basically a programming interface inside of Inventor that allows you to establish rules around your parts and assemblies. In this case, I want to edit my dialog box for making modifications to my drawer front. I'm going to create a new tab called Pull Width, which you can see appear on the right. And I want to establish rules that will be affected by this. Similar to the way in the eye part where I suppressed one hole or the other, I can go ahead and establish the distance between the two holes in the drawer front and build a quick pick dialog box out of it. Now that I have this finished, I can simply launch the dialog, go in and make any modifications, say to the drawer width, the drawer height, which size edge banding I want, and what drawer pull width I want, and we'll update the model directly using iLogic. Okay, make a quick change and it updates. Make another change and it updates. Very fast, very powerful. Here I have a part that's presently just a collection of surfaces. In traditional surface modeling, you have to trim surfaces into a wire-tight body to make a solid. With the Sculpt tool inside of Inventor, I pick overlapping surfaces and planes, and I'm able to define a solid body by selecting them. Here I'll pick this bottom plane. It shows the feet display in purple. Everything updates just the way I want it, and I'm able to generate a solid model. Here I have a plane set back into a more developed version of this. Now presently this is a single solid model. However, I want to develop this as though it were some sort of virtual assembly as a multi-body solid. So when I split this body, I will tell it to split it into multiple bodies. Now in the browser I can see I have solid 1, or solid 2, excuse me, which makes up my front, which I'll rename, and solid 3, which makes up the back part. I'm able to even select one of these bodies and change the color individually without affecting the other. So now I've got my front looking good. Maybe I want to make a modification. Let's go ahead and turn off my plane. Yeah, this is starting to look good. Let's make a quick modification to our back as well. In fact, let's go ahead and select a color that has a texture to it. There we are. Add a little more detail. Now you'll see we've gone a little farther. I've developed a grill feature. Now I want to go ahead and take and emboss text onto this curved surface. If I wanted this text to remain normal to the surface, I could use the wrap to face option. But in this case, since it's going to be injection molded, I'll leave that off so the faces are normal to my injection mold pull direction. I should go back and add a little draft to them, but that will wait for another time. You also need to be familiar with how to animate a presentation file. Presentation files are a way to create an exploded view of an assembly without making a mess out of your assembly. Here I am able to apply a tweak by selecting a couple of components and simply moving them away from the body. I can add additional components and again start dragging in a direction. Applying a tweak is very simple, but it creates an effective way of communicating. We can also override this value. Just simply hit the little checkbox and we'll update the view on the screen. We can continue working in this manner, deselecting components such as the washer or the vise plate, and going ahead and applying yet another tweak to the bolt. Now that we've got a lot of this taken care of, maybe we can clear these selections out and make a new selection set. For example, in this case, I'll select the shaft of the bolt. And then I'll select the bolt as the component. I'm going to change my transformation from a linear transformation to a rotational transformation of 720 degrees. Now that I have this done, I think we're in pretty good shape. Let's go ahead and let's take a look at how we can make this look a little more compelling. For example, moving into animation. Let's go ahead and play our steps. We see our bolt spin around, then slide down through the washer, pick up the washer and the plate stops, the bolt and the washer continue into place. Well, that's pretty good, but I want to make some changes. So I'll reset my scene, go into the list of sequences and start making modifications. For example, I'll take the rotational tweak and move it down so it's one of the last things, and I'll combine it with the last motion of the bolt and the washer into place and group them together. Now that I've done this, I'll just apply it and tell it to go ahead and play my animation forward and back. So now the bolt slides down into the washer. When the plate stops, the bolt starts spinning as it turns into the vise base. All right, that's much better, communicates more effectively, and gets what I'm trying to explain to others across clearly. But we can do a little better than this. We can add more. So let's change our browser to our sequence view. Each sequence of those steps has the ability to have additional information added to it. We can also hide particular components. In this case, though, we're just going to modify the speed in which an action takes place and set the camera. So the first sequence will hold this camera position. Now we can make modifications to the other sequence to make them more clear. So we'll reposition our model. That looks pretty good. And let's update sequence 3, and we'll set the camera to that value. When we go to animate this now, we can go ahead and select the little red dot icon and create an AVI or a WMV file of this presentation file as well. Set a fairly low resolution, but a fairly high bandwidth to create kind of a compromise video. And let's go ahead and play this forward and backward. So now it will go through the process of animating out our tweaks. It will show it turn in and then turn back out and re-explode our assembly. And update the camera views the way we set them. If you don't often work with sheet metal, it's important that you understand how to create flanges, annotate sheet metal parts in a drawing, create and edit sheet metal flat patterns, and also to be able to describe sheet metal features. Here we have a basic sketch. We can go in and we can start setting up our sheet metal defaults. Now, sheet metal defaults are also frequently referred to as sheet metal styles. It's a pretty obvious thing when you start looking at how the tool is used. For example, here we're going to establish a new style called aluminum 3mm. We make this style active, and we start editing how it works. For example, we can start making modifications to the material itself by selecting what material we want to use. We can go in and make modifications to the thickness, and start making modifications to things like the standard miter, seam, or rip gap. So we can tell it to just be the thickness divided by 2 or any specific number. Now there are several tabs in the sheet metal standards that deal with how to work with the basic material, how to display center marks in drawings, how to define relief shapes and what size reliefs that you want, what your bend radius might be. Once you've created one of these styles, you can save them to your library or export them as XML data to be shared with other users. This is particularly useful around the unfolding methods if you want to use something other than K-factors and want to work instead from a bend table. All of this gives you a lot of options in working with your real-world tooling. Okay. We can select which material we want to use, which default rule we're going to be actively using in the part. Now let's create a face. A face is basically like an extrusion for sheet metal. It just adds a thickness to a sketch. Let's apply a basic flange now as well. We do have some interesting options. For example, being able to add all the flanges around a loop, as we'll do in this case. All the flanges in just one step. We can establish the height of that flange. That looks good. And if we wanted to, with the icons around, we could change the bend radius from default or any gaps from default. Now that we've made this initial set of flanges, let's add some individual flanges at a different size. All I have to do is go around and pick the edges that I want to apply them to. One thing that I find is great is the fact that we'll automatically set in my mitered corners regardless of what the angle is. Now, if I want to, I can go ahead and make modifications to this. For example, I select my corner edit, and I'm able to override how this corner is resolved from being a simple miter to an overlap, and you can see the result on the screen. I can also swap out the other direction or tell it to just not generate it at all, but let's go ahead and keep that one. So as we make modifications, we're able to quickly update our model. It looks great. Everything is generated very, very easily. Now I want to make a flange of a different type. This is called a lofted flange. A lofted flange is also known frequently as a transition. So we're going from a round to a rectangle. We're able to control whether or not it's going to be bend, break, press, or die formed. You can see not only does the 3D model update, we also build in things such as tolerances. So we're going to allow the chordal deviation of up to 3 millimeters. That cuts down on the number of bends that we need to make this face. Now there's one problem with this, is we can't unfold it because it is a closed shape. So we need to be able to add a rip to this. So we can select 2 points, it will rip this open. Now we're going to be able to create a flat pattern to this if we choose to. Let's go back to our original model and tell it to generate the flat pattern, just because I want to show you some additional options. We can go in and annotate the bend order, so we can take the bend order that Inventor predicts and override it with one that we think is more suitable for our process. It clearly indicates through the use of icons which bend order elements we've overridden and made changes to. Makes it very easy for others who have to edit our geometry to understand what has and what hasn't been changed. Now let's go ahead and create some documentation. I tell it that I want to create a base view of my part. I select the component that I want to create a drawing of, and then I can select whether I want the folded model or the flat pattern. I can set my scale. If we were going to create working patterns out of this, I would probably go directly to DXF at 1:1 scale, which you can do in Inventor. It drops in my drawing view. All I want right now is the flat pattern. That looks just perfect. I want to be able to go ahead and add some annotation to this. Just like adding dimensions to any part, where we can add baseline dimensions, ordinate dimensions, what have you. Sheet metal has the ability to also get special dimensions. For example, bend callouts. So this callout was dropped directly on the flange. However, I can pull it out as a leader, and it will tell me what direction, what radius, what angle this bend is at. But with a more complex part like this, that can be somewhat difficult to decipher. So let's create a table. Because I have a flat pattern, Inventor automatically detects that I want a bend table. When it does, it labels each bend individually, gives me a table of the bend ID, the direction, the radius, and the angle. And if you look closely, you'll see that the overrides that we applied in 3D are still in effect in this 2D drawing. Another subject that not everyone uses is the weldment. If you're not familiar with the weldment, take a look at this video to try and understand a little bit more about it. The weldment environment inside of Inventor is a specialized environment. It's a subset of the assembly. What you do is you take an existing assembly and convert it, selecting the welding rod, the welding standard. This goes very closely with most working workflows where you have an assembly and you need to generate a single part file at the end. It also updates your assembly environment to include processes. For example, added to our weldment environment now is a preparation process. Once we've entered the preparation tools, we can apply things like chamfers to our models. So let's go ahead and chamfer our gusset. Now that we look a little more closely, we can see that the chamfers have been applied, but if we edit that original part, the chamfers are not on that original part. Now that part may be used in a number of different weldments, and this may be the only one where we ask there to be a preparation. The welds themselves are a different approach as well. We can add fillet welds, where we can select bodies and tell it to apply a weld of a certain size between them. We also have a design accelerator that can help us understand what size this weld needs to be. In this case, we'll just go ahead and apply this. That looks good. It even gives us the appearance of having a weld. It will also add mass to our assembly, which we'll take a closer look at in just a moment. Here, we're going to head and select another set, and we'll go ahead and select all the geometry that we want included so that this weld wraps in underneath onto that preparation. That looks great, but let's make it look a little better. Let's go ahead and apply an end fill, and that will update our assembly and have it just look just that much better and make it easier to understand exactly what we're looking for. We can also apply different types of welds. For example, the groove weld can be used to close in spaces. We can even do some fancy things. For example, here we'll select this hole and we'll select the pipe that's going through it, and we'll tell it to do a radial fill to bring in that gap. That looks nice, and now we can go ahead and apply other welds over the top of it. If we like, we can go in and take a look at the eye properties of our welds. We can go and validate that we're using the type of weld rod material that we want to use. We can override it if we want to, and we can get the physical properties of our welds. We can find out what the mass of all our welds are for the whole assembly. That includes cosmetic welds that just use an area and a type of weld. If we like, we can even generate an Excel spreadsheet that will tell us what our weld beads are down to the individual weld, so we can make sure that we're getting the right material. One other thing we can do with the weldment environment is generate documentation for each phase of the weldment environment. So for example, here I'll tell it to go ahead and generate a drawing set to a scale. And in this case, I want to go ahead and select the assembly state for my drawing. So this will be the raw components assembled together. I can tell it that I'd like to place another drawing view of the same assembly, or excuse me, in this case the same weldment, but in a different state. So we'll select the same file, we'll select the same position, the same color override, but this time we'll tell it to go ahead and show us what the post-weldment machining version looks like for our drawing view. So we can see a notch cut in the end, we can see all of the welds and the preparations in place, all in the same drawing. That allows us to more closely document our manufacturing process. Autodesk Inventor is an incredibly powerful program, and mastering it to the point where you can achieve professional certification is certainly a goal worth pursuing. You should now be able to identify the options available to you to prepare for certification. We've reviewed the certification objectives using several examples, and hopefully you're comfortable going back through the material and being able to pick out objectives that you're not familiar with. Now you should begin the process of preparing for the exam. As mentioned before, there are several resources for preparing for the exam. Autodesk.com/certification is a great first place to start. There are also official certification preparation materials available from Cybex and Ascent Publishing at the URLs listed on the screen. Finally, I'd like to thank you for taking the time to visit this virtual class. Wish you the best of luck with your Autodesk Inventor certification, and thank you very much for using Autodesk Inventor. Good day.